Today, we're diving into something that sounds like science fiction, but is absolutely real. The incredible science that lets us see directly inside the human body, uncovering all its secrets without ever making a single cut. I mean, it really does sound like magic, doesn't it? The idea that we can peek under our skin, look at our bones, our brain, our organs, all without a single incision. It's truly one of the greatest achievements of modern medicine. So, how on earth do we actually do it? Well, it all started with a surprisingly simple idea. The whole journey began with a concept we all understand: casting a shadow. But this isn't a shadow you can make with a flashlight. Oh no, this is something way, way more powerful. To cast this special kind of shadow, you need a special kind of energy called ionizing radiation. Now, this stuff is so powerful, it can literally just knock an electron right out of an atom. X-rays are a perfect example, and they were the very first key to getting that first amazing look inside our bodies. So, how does this energy actually create an image? Well, it all comes down to what gets through and what doesn't, a principle called differential absorption. Just think of it this way. Really dense tissue, like your bones, acts like a thick wall, and it blocks most of the X-rays trying to pass through. That's why bone shows up as white on the final image. But your soft tissues, like muscle, are way less dense, so more of the X-rays can pass right through them, which makes them look darker. It's essentially a super high-tech shadow picture. And this is a perfect illustration of that concept. What you're looking at is a mammogram, which is a specialized kind of X-ray. You can see so clearly how the different densities of the tissue create this incredibly detailed image. The lighter, whiter areas, that's the denser tissue. And the darker gray areas, that's the less dense, fatty tissue. All of that internal structure revealed by one powerful shadow. But a single 2D shadow has its limits. Things can overlap, they can hide behind each other. So what if you wanted to see more than just the shadow? What if you wanted to see a full three-dimensional slice of the body? Well, that's where things get really clever. So let's take that idea and level it up. Instead of just one shadow from one angle, what if you could take hundreds of them from every possible angle all the way around the body? And then, what if you could feed all of that information into a powerful computer and tell it to figure it all out? Well, that's exactly what a computed tomography scan, you probably know it as the CT scan, actually does. Let's break it down. First, an X-ray source and a detector spin around you, taking all those different projection images. Then, the detectors measure precisely how much the X-ray beam got weakened as it passed through your body from each of those angles. And finally, this is the magic part, a powerful computer takes all that data and reconstructs it into a stunningly detailed cross-sectional image, a slice. We're all used to thinking about images being made of little 2D squares called pixels, right? Well, a CT scan takes that to a whole new dimension. The image is built from 3D cubes called voxels, which is short for volume pixels. Each one of these tiny boxes represents a specific volume of real tissue and its measured density. It's like building a model of the body out of microscopic digital Lego bricks. And here you can see just how massive of a leap this technology was. On the left, there's that familiar X-ray shadow. But on the right, wow, that's a CT slice. The difference in the level of detail is just staggering. Instead of overlapping shadows, you get this crystal clear map of the internal organs. It's like the difference between seeing a building's silhouette and getting its full architectural blueprint. Now, X-rays and CT scans are incredible tools, but they both use that ionizing radiation we talked about earlier. So the next great leap in imaging was to figure out ways to see inside the body using completely different physical principles, with no radiation at all. And asking that question led to two totally revolutionary new technologies. First, what if we could map the body not with high-energy radiation, but with something as fundamental and safe as sound? This is the secret sauce behind ultrasound. It's basically sonar for the human body. High-frequency sound waves get sent into your tissues, and here's the key. They travel at different speeds through different materials. So when those sound waves hit a boundary, like, say, between your liver and your kidney, some of that sound echoes back. And by timing those echoes perfectly, a computer can build a picture. And this is the little device that does all the heavy lifting, the transducer. You can think of it as a very sophisticated speaker and microphone all rolled into one. It sends out a short little pulse of sound, and then it immediately switches into listen mode to hear the echoes that come bouncing back. The The time it takes for an echo to return tells the machine exactly how deep a structure is, creating this dynamic, real-time image right on the screen.
Okay, so we've used radiation and we've used sound, but for the most detailed, high-resolution map of all, especially for soft tissues like the brain or muscles, we need to go even deeper. We need to go down to the atomic level.
This is the first step in what's called magnetic resonance imaging, or MRI, and it's pretty mind-bending. See, our bodies are mostly water, so we are packed with hydrogen atoms. Each one of those has a proton at its center that acts like a tiny spinning magnet. Normally, they're all just pointing in completely random directions, but inside an MRI's incredibly powerful magnetic field, they're forced to align with it. They just snap into a low-energy state, all pointing in the same direction. Okay, so what happens next? A radio wave pulse is sent in, and it knocks all of those neatly aligned protons off kilter. But when the pulse stops, the protons try to relax back into alignment with the big magnet. As they do this, they release a tiny little radio signal of their own. The MRI machine is basically one giant antenna, listening for these incredibly faint signals. And here's the thing. Protons in different types of tissue relax at different rates and give off different signals. By mapping all those subtle differences, a computer can build an image of soft tissues with a level of detail that is, frankly, breathtaking. So we have shadows, we have slices, we have sound waves, and we have magnets. 4 incredibly powerful but very different ways to peer inside the human body. So how do doctors choose which tool is the right one for the job? This chart really brings it all together. If a doctor thinks you've broken a bone, the choice is easy: a quick X-ray, which is just perfect for seeing dense structures. Now, for a more detailed look at organs or maybe a really complex fracture, they'll turn to a CT scan to get those incredibly detailed slices. When safety is absolutely the top priority, like for viewing a developing fetus, ultrasound is the clear answer, using totally harmless sound waves to see soft tissues and even blood flow. And finally, for the most detailed map of soft tissue you can possibly imagine, think the brain, muscles, or ligaments, the MRI is the absolute gold standard. And just notice that really important difference in the last column: only the X-ray and CT scan use that ionizing radiation we started with. You know, when you step back and look at the big picture, it's just incredible. In just over a century, we've gone from capturing these faint, simple shadows of bones to creating these detailed, beautiful magnetic maps of our very own atoms. It's a remarkable journey of human ingenuity. And it really makes you wonder, what's next? What will the next generation of imaging allow us to see?